providing adequate overcurrent protection for a transformer is crucial for its safe and reliable operation. The situation presented involves feeding a 75 kV transformer with a primary voltage of 120/208 volts and a calculated primary current of 208 amps from a 200 amp fused disconnect. According to standard electrical practices in the National Electrical Code, this configuration is generally not acceptable because the overcurrent protection device, in this case the fused disconnect, must be sized appropriately to protect the transformer from overloads and short circuits. The primary concern here is whether the 200 amp fused disconnect provides sufficient protection for the 75 kV transformer. The National Electrical Code, or NEC, provides specific guidelines for transformer overcurrent protection to ensure safety and prevent damage. Let's delve into the key considerations for sizing the overcurrent protection for this specific transformer. Firstly, calculating the transformer's full load current is essential. The full load current on the primary side of the transformer is determined by the transformer's kilovolt-amps rating and the primary voltage. The formula to calculate the primary current is kilovolt-amps times 1000 divided by the square root of 3 multiplied by the voltage. In this case, it's 75 kV times 1000 divided by the square root of 3 times 208 volts, which equals approximately 208 amps. Secondly, the NEC mandates that the overcurrent protection device, such as a fused disconnect or circuit breaker, be sized no greater than 125% of the transformer's primary full load current, unless specific conditions apply. This requirement is in place to accommodate the inrush current that transformers experience during energization, as well as to provide adequate protection against sustained overloads. Thirdly, applying the 125% rule to the calculated full load current of 208 amps, the maximum allowable overcurrent protection would be 208 amps times 1.25, which equals 260 amps. This means that the overcurrent protection device should be rated at or below 260 amps to comply with the NEC requirements for transformer protection. Fourthly, since the existing fused disconnect is rated at 200 amps, it falls below the calculated maximum allowable overcurrent protection of 260 amps. This indicates that the 200 amp fused disconnect may not provide adequate protection for the transformer, especially considering the potential for inrush current and sustained overloads. Fifthly, the NEC permits the use of the next higher standard overcurrent device rating if the calculated value does not correspond to a standard size. However, it's crucial to ensure that the next higher standard size still provides adequate protection for the transformer and does not exceed the maximum allowable overcurrent protection specified in the code. Sixthly, in this scenario, increasing the fused disconnect size to the next higher standard rating, such as 225 amps or 250 amps, may be considered, provided that it does not exceed the calculated maximum of 260 amps. However, it's essential to evaluate the specific characteristics of the transformer and the application to determine the most appropriate overcurrent protection size. Seventhly, the selection of the overcurrent protection device should also take into account the transformer's impedance and the available fault current at the installation location. These factors can influence the magnitude and duration of fault currents, which in turn affect the ability of the overcurrent device to effectively protect the transformer. Eighthly, it's important to consider the coordination of overcurrent devices within the electrical system. Coordination ensures that the overcurrent device closest to the fault or overload will trip first, minimizing disruption to the rest of the system and preventing unnecessary outages. Ninthly, if the existing 200 amp fused disconnect is deemed inadequate for protecting the transformer, it should be replaced with a properly sized overcurrent protection device that meets the NEC requirements and provides adequate protection against overloads and short circuits. Tenthly, before making any changes to the electrical system, it's crucial to consult with a qualified electrical engineer or licensed electrician to ensure compliance with all applicable codes and standards. They can perform a thorough assessment of the system and provide recommendations for the most appropriate overcurrent protection solution. 11thly, The physical space constraints mentioned in the scenario should be taken into consideration when selecting the replacement overcurrent protection device. If there is limited space for a larger fuse disconnect, alternative solutions such as using a compact circuit breaker or a different type of overcurrent protection device may need to be explored. 12thly, another option to consider is the use of a transformer with a lower kilovolt amps rating that would allow the use of the existing 200 amp fuse disconnect. However, this would require careful evaluation of the load requirements to ensure that the smaller transformer can adequately serve the connected equipment. 13thly, it's also important to verify the voltage rating of the fuse disconnect to ensure that it is compatible with the primary voltage of the transformer. Using a fuse disconnect with an incorrect voltage rating can pose a safety hazard and compromise the protection of the transformer. 14thly, the ampacity of the conductors feeding the transformer must also be considered. The conductors should be sized to carry at least 125% of the transformer's primary full load current, and the overcurrent protection device should be sized to protect the conductors as well as the transformer. 15thly, the type of fuses used in the fuse disconnect should be selected based on the transformer's characteristics and the application requirements. Time delay fuses, for example, may be used to accommodate the transformer's inrush current without nuisance tripping. 16thly, it's crucial to ensure that the fuse disconnect is properly installed and maintained. This includes verifying that the fuses are correctly sized and installed, and that the disconnect is free from any damage or corrosion. 17thly, regular inspections and testing of the overcurrent protection system should be performed to ensure its continued reliability. This can include visual inspections, insulation resistance testing, and functional testing of the fuse disconnect. 18thly, documentation of the transformer's overcurrent protection system should be maintained, including the transformer's nameplate data, the calculated full load current, the size and type of overcurrent protection device, and any relevant test results. 19thly, training should be provided to personnel who are responsible for operating and maintaining the transformer and its overcurrent protection system. This training should cover topics such as transformer operation, overcurrent protection principles, and safety procedures. 20thly, it's important to stay informed about changes to the NEC and other relevant codes and standards. The electrical industry is constantly evolving, and it's crucial to keep up with the latest requirements to ensure compliance and safety. 21st, in some cases, it may be necessary to install additional overcurrent protection devices, such as secondary side fuses or circuit breakers, to provide comprehensive protection for the transformer and the connected equipment. 22nd, the use of a transformer monitoring system can provide valuable information about the transformer's operating conditions, such as voltage, current, and temperature. This information can be used to detect potential problems early on and prevent costly failures. 23rd, it's important to consider the environmental conditions in which the transformer is installed. Transformers installed in harsh environments, such as those with high temperatures or corrosive atmospheres, may require special overcurrent protection measures. 24th, the use of surge protection devices can help to protect the transformer from voltage surges caused by lightning or switching events. Surge protection devices should be installed on both the primary and secondary sides of the transformer. 25th, it's important to ensure that the transformer is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock hazards. 26th, the use of a ground fault protection system can help to detect ground faults and prevent electrical fires. Ground fault protection systems are typically required for transformers serving large loads. 27th, it's important to consider the impact of harmonics on the transformer's overcurrent protection system. Harmonics can cause the overcurrent protection device to trip prematurely, or they can mask the presence of a fault. 28th, the use of a harmonic filter can help to reduce the levels of harmonics in the electrical system and prevent problems with the overcurrent protection system. 29th, it's important to consider the potential for motor starting currents when sizing the transformer's overcurrent protection device. Motor starting currents can be several times higher than the motor's running current, and the overcurrent protection device must be able to withstand these currents without tripping. 30th, the use of a soft starter or variable frequency drive can help to reduce motor starting currents and prevent problems with the overcurrent protection system. 31st, it's important to consider the potential for transformer overloading when sizing the overcurrent protection device. Transformer overloading can cause the transformer to overheat and fail. 32nd, the use of a transformer thermal monitoring system can help to detect transformer overloading and prevent damage. 33rd, it's important to consider the potential for transformer failure when designing the overcurrent protection system. Transformer failures can be caused by a variety of factors, such as insulation breakdown, winding shorts, and core damage. 34th, the use of a transformer differential protection system can help to detect transformer failures and isolate the transformer from the electrical system. 35th, it's important to consider the potential for arc flash hazards when working on or near transformers. Arc flash hazards can cause serious burns and other injuries. 36th, the use of arc flash protective clothing and equipment can help to protect workers from arc flash hazards. 37th, it's important to follow all safety procedures when working on or near transformers. Safety procedures should include energizing the transformer, grounding the transformer, and wearing appropriate personal protective equipment. 38th, the NEC provides specific requirements for transformer overcurrent protection in Article 450. It is important to consult this article for detailed information on the code requirements. 39th, the overcurrent protection device should be readily accessible for inspection and maintenance. The location of the overcurrent protection device should be clearly marked. 40th, the overcurrent protection device should be properly labeled with its ampere rating and interrupting rating. The label should be durable and easy to read. 41st, the overcurrent protection device should be inspected regularly for signs of damage or deterioration. Any damaged or deteriorated overcurrent protection devices should be replaced immediately. 42nd, the overcurrent protection device should be tested periodically to ensure that it is functioning properly. The testing should be performed by a qualified electrician. 43rd, the results of the overcurrent protection device testing should be documented and kept on file. The documentation should include the date of the testing, the results of the testing, and the name of the person who performed the testing. 44th, the overcurrent protection device should be replaced at the end of its service life. The service life of an overcurrent protection device is typically determined by the manufacturer. 45th, the overcurrent protection device should be disposed of properly. Overcurrent protection devices may contain hazardous materials and should be disposed of in accordance with all applicable regulations. 46. It is important to consult with the transformer manufacturer for specific recommendations on overcurrent protection. The transformer manufacturer may have additional recommendations based on the specific design and application of the transformer. 47. The overcurrent protection system should be designed to protect the transformer from all credible fault conditions. The fault conditions should include short circuits, overloads, and ground faults. 48. The overcurrent protection system should be coordinated with other protective devices in the electrical system. The coordination should ensure that the overcurrent protection device closest to the fault will trip first. 49. The overcurrent protection system should be designed to minimize the impact of a fault on the electrical system. The design should consider the voltage dip caused by the fault and the potential for damage to other equipment. 50th. The overcurrent protection system should be designed to be reliable and maintainable. The design should consider the ease of inspection, testing, and replacement of the overcurrent protection devices. In summary, a 200 amp fuse disconnect is likely insufficient for protecting a 75 kV 208 volts transformer with a primary current of 208 amps. A larger disconnect, potentially 225 amps or 250 amps, may be required, but careful evaluation and consultation with a qualified professional are essential.